you can post them in the Q&A by scanning that QR code, and then, you know, I'll address them whenever I see them. So now, what if the capacitor, what if the dielectric inside the capacitor, between the conductors is a combination of two dielectrics? Either they're stacked vertically or they're stacked horizontally, okay? So here, you can model this one as one capacitor being in series with another one. So we can call this C1, we can call this one C2. Okay, and here we can say our total C, because these are in series, is 1 over C1 plus 1 over C2. And then here, C1 is epsilon A over D of that capacitor. So it's epsilon 1 over D1. And then C2 is going to be epsilon 2A over D2. Okay? And then here we can say, okay, so our total C is going to be 1 over C1, which is D1 epsilon 1A plus D2 epsilon 2A. And that is going to be epsilon 1 epsilon 2. Nope. That is going to be epsilon 2 D1 plus epsilon 1 D2 over epsilon 1 epsilon 2A. And the total capacitor is going to be epsilon 1 epsilon 2A over epsilon 2 D1 plus epsilon 1 D2. Okay, and then in this case, you can say, okay, what if I replaced those two dielectrics with something else? I modeled all of this with a material that has an effective permittivity. So we're combining all the epsilon 1 and epsilon 2 with the thickness of D1 and D2 respectively to find an effective permittivity. So here we can say, okay, in general, C should have been epsilon A, or let me just put that here. It should have been epsilon effective multiplied by A over D, where D is in fact D1 plus D2. So D1 plus D2, this is epsilon effective A. And as you can see, this is epsilon 1, epsilon 2A for epsilon 2 D1, epsilon 1 D2. So this way, you can even find, you know, what is the effective permittivity of these two materials being stacked together with two different thicknesses. So here, if we simplify this, so we found C. That's the end of our problem. But here, we can model this and say epsilon effective is in fact D1 plus D2, epsilon 1, epsilon 2, epsilon 2 D1 plus epsilon 1 D2.
Is epsilon effective just the total epsilon?
It's like, yeah, the effective, if you had to replace both of those, dielectrics with just one.
So it's the equivalent of both of them, like?
Yes, both of them with that thickness, with the thickness of D1 and D2. Okay? Because sometimes it happens that you need, a certain permittivity for your application, okay? But then that permittivity doesn't exist with natural material. What you can do is to stack them either vertically stack two materials that are available, vertically or horizontally, to get to the permittivity that you want. Okay? Go ahead.
And then when we write C in terms of the effective, why does the epsilon 2 and epsilon 1 on the denominator go away?
Why do they go away?
Yeah.
Do you... Oh, here?
Yeah.
Okay, so I'm going to say, okay, let's assume that this was a parallel plate capacitor with a dielectric, that dielectric had an effective permittivity. Let's call it epsilon effective. It can be any name, right? And then if I had only that, okay, I had a slab of dielectric, then the capacitance of that parallel plate capacitor would be epsilon A over D. That's always true. Epsilon of the full slab. So that's why it's not a, first, I'm not writing it as a function of epsilon 1 and epsilon 2, but later, because I found it in terms of epsilon 1 and epsilon 2, I'm relating the two. Because I'm like, these two should be the same. They're equivalent. Okay, now let's go to this one. This one is, when you have them horizontally stacked, they're like parallel capacitors. Because if you assume that these 2 points are the same conductor, then the voltage on both of them is the same. And when you have two components that their top voltage and the bottom voltage is the same, they are in parallel. So this is C1, this is C2. Now C1 is epsilon 1 A1 over D. And here C2 is epsilon 2 A2 over D. And the total C here is C1 plus C2 because they are in parallel. So it's going to be 1 over D epsilon 1 A1 plus epsilon 2 A2. And I'm going to call this, let's say, epsilon effective series, and then I'll call this one epsilon effective parallel. So we know that in each of these, you can have a different epsilon effective. Okay? Now, I found C total, so that's the end of this question. But if I wanted to replace, have one signal slab there, then this C total would be equal to A epsilon effective parallel over D, where A is A1 plus A2. So that way you can say epsilon effective when the two dielectrics are in parallel together is going to be epsilon 1 A1 plus epsilon 2 A2 over A1 plus A2. That's another kind of thing to know. You wouldn't be asked to drive these two, but it's just good to know that, sometimes, yes, you can create new permittivities, even if that material doesn't exist in nature. Okay, you can combine natural materials together and create that. Okay. Any questions? Mm-hmm.
Is it possible to have a circumstance where there's like two on top, two on bottom, and we could, like in that case, would we be able to do it either way?
Like a 2 by 2.
Yeah.
Yes, the same way though. Yeah. Okay, let's solve this example. Okay, I'm going to start from the beginning. This looks like a midterm example where you would find V, E, the capacitance value, and then also the charges that are induced on the conductors. Okay, So here we have two conductors with the radius of A and B. And then the dielectric in between them has a permittivity of epsilon r. And then we are, again asked to find V, E, and then the total charge induced, and then the capacitance. Okay, so we're going to start with that. Any suggestions? How can I find V?
Use the Laplacian.
Yeah, whenever you see boundary conditions, whenever you see you've given two voltages, here we've given that on the conductor A, voltage is V naught, on conductor with the radius B, voltage is 0. Immediately think of Laplacian equation. So let's do that. And then, so Laplacian of V is 0. Okay. Then, do you remember what we did here? Which coordinate system should I use? Spherical. In general, in a spherical coordinate system, V is a function of what variables? R, theta, and phi. How about now, here? Here, we have on the first sphere, the smaller one, the voltage is V naught. On the bigger one, it's 0. From these two boundary conditions, you can tell that V is not a function of theta or phi. It's just a function of radius. Okay? So we are going to say V is a function of radius, VR. And now, when we look at the spherical, the Laplacian in the spherical coordinate system, if V is only a function of R, then the Laplacian is equal to R being 0. So this means that this has to be a constant number, C1 prime, let's say. And then that would mean that the derivative of V to R is C1 prime to R2. So now if I want to find V, that would be C1 over R. I'm just ignoring the minus here. If you want, you can include it. But C1 is minus of C1 prime, let's say. C1 plus C2. I'm just introducing a new variable. Now, I use the boundary conditions. I know that V at R equal to A is V naught. And then V at R equal to B is 0. Let's just start with 0, so that would be easier. That would mean C2 is minus C1 over B. And then C1 over A plus C2, which is minus C1 over B, is going to be V naught. So C1 is V naught A, B, B minus A. I think so, yeah. And C2 here is minus V naught A, B minus A. So we found V to be a function of R such that it's V naught A, B, B minus A, 1 over R, minus V naught A, B minus A, or V naught A, B minus A, B over R minus 1. Does it make sense?
Sorry, can you explain how you found C1 and C2? Why did you plug in like C2 is equal to negative C1 over B?
let's take the derivative of v. That's minus c1 over r squared, right? Okay. So I'm just saying, at the beginning I knew it's a constant, right? If you want, you can keep it. You can keep it as c1 prime, right? It's just that like you have to consider a negative later. And then, so I'm going to call this c1 prime. If you didn't, it's okay. You can, you can just, let's do this one. Let's call this one c1 and not change it. This would be c1, and then here it's a minus c1. It would be exactly the same thing. Here we would have minus c1 over a, minus c1 over b, and then here c1 would be,
How come C1 isn't a?
no, here then it would be plus c1, and this would be plus, right?
How come there's C1 in the first equation? Shouldn't it be C2?
I just found c2, I just skipped one step. I put c1, c2 here. I found c2 here first, and then plugged it in here. Okay? The only thing would be this would have a negative thing, and because it is negative, it's going to be positive. And then this would have a negative as well. Plus. Yeah, there wouldn't be any, there shouldn't be any difference. Okay, so we found V. Now let's find E. How do we find E?
Negative gradient of v.
Thank you, yes. And since V is just a function of R, it's quite easy. We just need to take the derivative and then the derivative of V in R hat direction. So that would be V naught A, B minus A, and then minus B R squared, R hat. So this is going to be minus, and then there is a minus here as well. So it's going to be plus V naught AB, B minus A, 1 over R squared, R hat. And that's our A. Does it make sense? Yeah? Okay. Okay, so we found V, we found E. We still need to find the total charge induced and then the capacitance. Okay? So it's kind of like by putting the order like this, it's guiding us how we should be solving it too. We found, if they told us like find the capacitance without telling us find V, E, and all of those things, we would have taken exactly the same steps. Okay? So now, let's go find the total induced charge. Any suggestions how we would find that?
Yeah.
Gauss's law? Okay, that's one. Yes, perfect. Easier one?
We do E times epsilon naught, and then we find rho s.
Yes, that's the easiest way to do this. Gauss's law is perfectly fine, because you have E, you can find D, and then D dot ds, you take the integral, and then you would find Q. But if you don't want to take the integral, then you know that rho s at r equal to b is E epsilon E at r equal to b, the amplitude of it. Let me write it the other way so you're not, it's not confusing. So E at R equal to B is rho S over epsilon n hat. And n hat is minus r hat direction. So that would give us rho S at point B. The same is true here. If we were looking at right here, E at R equal to A, right at the boundary here, it's rho S at R equal to A over epsilon n hat. N hat right here is in R hat direction. So you can use any of these to find the rho S either on the bigger conductor or the smaller one. Doesn't matter which one, really. So let's go here. We found E. Okay, so this is our E. Now, we said, let's do this one. E at R equal to A is rho S at R equal to A over epsilon in R hat direction. So let's plug in R as A here. That would be V naught B, B minus A multiplied by A. So that way, rho S at R equal to A is epsilon V naught B over A, B minus A. And now you can say, okay, Q is going to be rho S ds. And since rho S is constant, it's simply going to be epsilon V naught B A B minus A multiplied by the surface of sphere A. Just remember, this is the last part that can mess it up. You're doing this, you found rho S over the inner conductor, and now in order to find Q, you're integrating rho S ds on that inner conductor. So this is going to be 4 pi A 2, right? That's the area of a sphere, 4 pi A squared. So 4 pi epsilon V naught A B B minus A. And then next, C is simply Q over V. So 4 pi epsilon A B B minus A. Any questions? Let's see if we would have got the same answer if we were doing this on the outer conductor, okay? So on the outer conductor, E at R equal to B is minus rho S over epsilon R hat, because it's the other direction. And this is R rho S. I always forget to put this one. Minus rho S at R equal to B over epsilon R hat. Now, let's plug in R equal to B in our E formula. And this is R between A and B. There is a minus here, so we put the minus, right? No, sorry, it's in the r hat direction, but this is correct now. Now, rho s r equal to B is going to be epsilon V naught A B. One of the B's are going to cancel each other. B minus A multiplied by B. Right? And then we do Q to B, and here is a minus, so we would find minus Q when epsilon V naught A B minus A multiplied by A is 4 pi B squared. We are multiplying by the surface of the outer conductor. So again, we would get 4 pi epsilon V naught A B B minus A. So we just showed that the Q that is on the inner conductor is exactly the same and opposite of the Q on the outer conductor. Right? Does it make sense? Are we good? Okay. So this is, let's see how much we are left. Okay, we don't have much left. So we can solve this ourselves too. Like in this case, is this a parallel stacking or the series stacking of the two capacitors? Series, exactly. They have a common voltage point, so it's going to be series work. Huh?
Can you explain how this is series?
So you have, let's say this is your voltage 1. Let's say this is our ground. Then we have a common voltage here. And then this is our V naught. V naught, let's say, right? Whenever you have a common voltage between the two series. In this one, you have a voltage here between the two conductors, and then you have another one here. So that's why the two are parallel.
Wait, so if the
I'm listening to you. Yes, go.
where, how come the first two have a common voltage? You repeat.
They have a common voltage right here. It's the same interface, right?
If it's the same interface, then
So the voltage is going to be one number at that point. And both capacitors have access to it.
it's one surface shared by one.
Mm-hmm.
Oh, okay.
Okay.
Right.
Okay. So now the only thing we should know is that, okay, so if you go back here, the capacitance was 4 pi epsilon, right? 4 pi epsilon multiplied by the radius of the inner and outer over the difference between the two radius. So let's bring this one here actually, so we remember it. So this is our general one. So in configuration A, C1 is going to be 4 pi epsilon, it depends which one we call. Let's say epsilon 1. And then now we need to find the radius around epsilon 1, the radius of the two conductors. Here, this is C. The radius of the other one is B, C minus B. and C2 is 4 pi epsilon 2 AB, sorry, AC, for some reason this is called C, AC, and then C minus A. So C of series is going to be 1 over C1, 1 over C2. In configuration B, this time we can't use this formula because we only have half of the sphere, right? What do you think would change if we had half of the sphere?
The enclosed charge, maybe.
How would it change?
It would be different on both surfaces because they have different epsilon values.
So here we have a minus Q, let's say, or plus Q, minus Q here, and then plus Q here, right? If that's what you mean. The only difference is that now, instead of the full sphere, or kind of like a hollow sphere, you have half of it. So this would be like a 2 pi, C1 would be 2 pi epsilon 1 A B, B minus A, and then C2 would be 2 pi epsilon 2 AB, B minus A. So you're taking half of the surface of the inner conductor, basically, to find Q. And then C parallel is C1 plus C2. So because if you have Q here, half of it would go here, and then some of it would go here. Okay, but this is honestly like this is too much. But anyway, so now let's talk about electrostatic energy. Okay, we from the beginning we said capacitance help us store energy. Now it's time to say how much that energy is. Okay, voltage is, we defined it before, is the amount of work we would do per unit charge, per coulomb. And then I can't see you. Per coulomb. And so we can use that definition to find what the work we are doing. And the work we are doing is the work that is going to be later stored in the capacitance. Right? So we can say dWe here is going to be V dQ. And then we know that capacitance was Q over V. So we can define V as Q over C. I don't like it. Yeah, one way is to do it that way, basically. So let's do it. dWe is V, and then dQ, or sorry, we found V. So it's Q over C, and then dQ. And then here we can say WE is the integral of dWe, which is going to be integral of 1 over C Q dQ. If you're integrating over Q, what is that going to be? Okay. Q squared over 2, 1 over C, right? So WE is 1 over 2 Q2 over C, or 1 over 2 Q over C was V, Q, V. Or you can show it's C, V2. All of these are equivalent. So once you found C, right, for the same examples we solved so far, you might be asked, okay, how much energy you're storing? And then once you know the capacitance and you're given the voltage difference across the two, then you can find how much energy you're storing in that capacitance. Okay. Another way to show this is WE 1/2 integral of D dot E dV. This is another way, but it wouldn't require vector calculus identities, basically, to drive it to this point. Okay. If you like a brain teaser, you can try this. Try this. Just, okay. This would end our capacitance topic, okay? But I have something fun for you. Before we close the topic of conductors and dielectrics, do you know why cars and planes are safe from lightning? Like, you know, like you can be in the plane and there is lightning, but you don't die. Right?
Because we're sitting on chairs that aren't made of
You're sitting on chairs or what?
I wouldn't let that happen.